Hello and welcome to another video. In this video we're going to be working on largest combinations with bitwise and greater than 0. And in this one, the bitwise and of an array in nums is a bitwise and of all the integers in nums. So if you just have some array, you just do the whole bitwise and you're given an array of candidates and you want to evaluate the bitwise and of every combination, and you want to get the size of the largest combination of candidates with bitwise and greater than 0. So if you take a look at these examples, this one has a bitwise and of 16, which is greater than 0. So all you really care is this not 0, which it's not 0. I mean, this is 4 numbers, so this is your answer. This is the best. And then I guess there's other ones that have the same thing, so there's also like this one and so on, but there's nothing bigger than 4. In this one, 8 and 8 have a bitwise and that's non-zero. So I guess I kind of wanted to make a general framework you can use to solve these problems, and then we can like do that. And I'll try to do this in like all the problems. So the very first thing you can do is you can look at the constraints. And so the constraint is 10 to the 5th. So on LeetCode, HackerRank, all these things, think something like 10 to the 8th fails, 10 to the 7th passes roughly. So for 10 to the 5th, we know already we can't have n squared or worse, right? So we need to have basically n log n or better. So some common stuff, like for 10 to the 5th, you need n log n. For 1,000, you can have n squared log n, and so on, right? So just do the math, and then 10 to the 7th passes, 10 to the 8th doesn't. So we know we need n log n or better. We can't have anything worse. And then you want to go into like how do you solve this problem? Well, first of all, like you want to try to understand like how does a bitwise and work? Like how do I get a bitwise and that's non-zero? Like what criteria do I need? So for bitwise and for non-zero, let's just say we have some random numbers, like this is one number, this is another number. For a bitwise and, the way a bitwise and works is it ands every single bit and then it gives you the answer, right? So it'll and like this bit and this bit, give you an answer at this bit and this bit and so on. It's basically like the same as like an addition, you know, you do the same bits for each number. And the bitwise and, so 0 and 0 gives you 0, 1 0 and 0 1 gives you 0, and 1 1 gives you 1. So non-zero and, like for a number to be non-zero, it means one of the bits has to be a 1, right? That's the definition of non-zero. So you know that as long as one of these bits in the result is a 1, you're good. And in order for a bit to be a 1, I have to have a 1 bit in both, right? So here, like these two, like when I and these two, this will be 0, this will be 0, this will be 0, but this will be 1. 0 0 0 0 0 0. So as long as there's one set of bits that are the same, that are both a 1, you'll get a non-zero number. And so that's kind of basically what it is. And if you have 3 numbers, it's the same thing. You're going to and all 3 of them, and you need 1 bit in, you know, 1 bit in all of them to be non-zero. So in this case, there's a 1 everywhere here. And if this didn't happen, then this would be 0. So basically, for an and of n numbers, we need 1 bit at least in all of them to be a 1, and it has to be in the same location, right? So the same location bit for all of them has to be a 1. And so that's what we can use. So basically what we can do is we can go through this array and we can just record like the location of a bit and if it's 1 or not. So what we can do is we can, for example, for this, take every number and take its bitwise, like it's turn it into binary, and then figure out which bits are zeros, which bits are ones, and then we can just store that in an array. So for example, 16 is 16, and then no 8, no 4, no 2, and then no. Actually, this would probably be easier in an array. Yeah, let's just do that. So let's have something like this. And then, yeah, so this, okay, something like this. So it'll be, yeah, it'll be 0, 0, 0, 1. And then we can write down the bits here, I guess, and move this over. So we could say this is like the 1 value, the 2. Yeah, actually, you can even move this up here and make another one. Yeah, there you go. Okay. So this basically represents 1, 2, 4, 8, 16, 32, 64, something like that. Okay, so this is 16, 17. So I guess 16 actually should be this. 17 is this. Yeah, and then 71. So 71 has a 64. No 32. No 16. No 8, and I think it's like this. 62 is no 64. And then everything else is like a 1. So 1, 1, 1, 1. Think like this. Even if I'm wrong, it doesn't really matter because like this will be fine for the example. And then 12 is 0, 0, like this. And then 24 is 0, 0, 0, 1 here. Yeah. And then we won't even use the 14, doesn't really matter. Let's say these are numbers. So we'll have an array of like these totals. So we can have this on the top, maybe. And we can get rid of these numbers now because they don't really matter. We just need these. And so here we have a 2, here we have a 1, here we have a 3, 3, 4, 1, 1. So because we have a 4 here, we can basically say, okay, every number that has this number on, we can just AND those together and then we'll get a non-zero number. So this one, this one, this one, and this one. Actually, wrong one. Actually, no, the right one. Yeah, this thing right here. So that's essentially what we can do. And then to get a number and to get this array is pretty simple as well. Like let's say our number is 71. We can show how to build this array really quick. So basically we're just going to maintain like the index of what bit we're on and then just keep modding it by 2. So we're going to have this. And so we'll start here. So we'll say like we're on the index 0. Does this have a 1 at the end? Yes, it does. And then we will divide by 2. So 71 divided by 2 is 35. And we'll floor divide. Does this have a 1? Yes. And then divided by 2 again. So if this is 4 divided by 2, it'll be 17. Yes. 4 divided by 2 again. 8. No. 4. No. 2. No. And a 1. Yes. So this should be 71. Yeah, and it's this thing right here. Yeah, so that's pretty simple. Like you just keep dividing by 2 and you keep taking the bit and you do that. And then you'll have this like total array, and then whatever the biggest number is in the array is your result. So in this, we'll just return that. So hopefully that makes sense. Yeah, let's code that. So we'll have these totals, and because the number is 32 bits, we'll just make a 32 length array. So we'll say like, yeah. Okay, and we're gonna go through all these numbers. Keep track of an index. Either way, it doesn't matter which way, we'll make it like this. So we'll say while number is non-zero, bit counts I plus num and 1. So just check if the last bit's a 1, and then shift it to the right by 1. So just keep doing that. That'll fill out that array. Yeah, and then we'll just go through that array. Yeah. And return it. So just get the biggest number there and return it. So pretty simple. Hopefully I didn't screw anything up. Guess I did. Let's see. Oh, misspelled that. Also forgot to increment I. So let's do both of those. I need to increment I, not there, in here. All right, there we go. Okay, so pretty simple. So this is linear, and one space because only 32. So that's it. Hopefully it was helpful. If you did like the video, please like it and subscribe to the channel, and I'll see you in the next one. Thanks for watching.